So we want the instantaneous velocity at t equals 1. And we can symbolize that like this, where the prime means an instantaneous rate of change, the derivative. So a rock is dropped from a height of 64 feet. They give us the function for how fast it's changing. So it looks like we can jump right to the formula. We want the limit as t approaches 1 for s of t minus s of 1. So this is the value when we plug in 1 into the function. So that's negative 16 plus 64. That's 48. Divided by t minus 1. Just using what was the top of there's two limit definitions of the derivative. I used the top one in a previous video. Same as what's in your text. Just double checking something. Okay, I want to make sure I did that math right. So this is the limit as t approaches 1 of negative 16t squared plus 64 minus 48 gives us 16. And then we get t minus 1 in the denominator. So you can factor out negative 16. And let's see, factor out the negative 16 from this term here to make the squared term positive. That helps factoring be a little bit more clear cut. And so that parentheses that's left over is factorable. You can do t, that's one of the special ones, t minus 1, t plus 1. Because these multiply to make t squared minus 1. And so these cancel out. And so we're left with the limit as t approaches 1 of negative 16t plus 1. So if you're to, now we can plug in 1. Before we had to divide by 0 error, but if we plug in 1, you've got negative 16 times 2, that makes negative 32. So that's instantaneous velocity. We're decreasing at 30. The position of an object moving along a straight line is modeled by this function. We're supposed to find the average velocity over these intervals. So from x equals 1 to x equals 1.1. From x equals 1 to x equals 1.01. And so when we find average velocities, they're getting closer and closer together. That's simulating a slope at an instant, right? Because that's what the formula does. It finds the slope between 2 points that are infinitely close to each other. So for t is 1.1, well, actually, first what we want is to know what what the value for s is when t equals 1. If you plug in 1 into this function, 1 to the third is 1, so negative 1 minus 5 is negative 6. So at t equals 1, we get negative 6 for a value. So when t equals 1.1, the right side of the endpoint, 1.1, oh, come on, 1.1 to the third, and then that's negative because the negative's on the outside, minus 5. So we get this for a y value. So if we subtract that by our negative 6, and then divide that by 1.1 minus 1, so that's divided by 0.1, we get a slope of negative 3.31. And you'll just want to continue like that. Okay. Now we're using t equals 1.01. So we need the y value that corresponds to that. So raise that to the third power. That's negative, and then subtract 5 from it. So there's our y value. We got to subtract that from the y value when t equals 1. So subtract that by the negative 6. And then divide that by the distance between these 2 points. 1.01 minus 1 is 0.01. So we get negative 3.0301. So you can probably see where this is going. Getting closer and closer to a slope of negative 3. Just to finish it out, 1.001 to the third power, that's negative, subtract that by 5, and then we subtract that by negative 6, and divide that by 0.001. So the decimals will probably be important in this one. 6 decimal places. So 1, 2, 3, 4, 5, 6. I'm going to cut that one off because I said 6 decimal places. And then the last one, raise that to the third. Negative minus 5, so subtract that by a negative 6, which means add 6. So we get negative 3 point blah, 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 blah. I think that's 6 decimals. 1, 2, 3, 4, 5, 6. Ooh, shoot, I cut off an extra decimal there. I gotta do that one again. Because my heart is going to be broken if I get this wrong and I have to do it again. Oh, it already had 6 decimals. Okay. Okay, so it looks like the slope is getting infinitely close to negative 3. Man, I hope I didn't type anything wrong. Okay, phew. That one just, when there's a table, it takes a while.